Okay, ladies and gentlemen, I'm sort of, hitting on some issues we didn't have time to talk about because we drove through last time to a set of issues. So I'd like to finish up some of our discussion last time, and we're going to come back. This is normally, because I wanted to get you material for the take-home exercises, I'm hitting this in a somewhat different order, and I apologize for that. We are going to now talk about this construct, the kind of odd man out last time. We talked last time about map. What is map's job in life? Given a container, say a collection, what does it do? It takes in a what? If you call it on a container, say a collection, what does it take in?
Each element.
It takes in a function, and what does it return?
A container where that function is applied to each element in the container.
That's right.
Sorry.
Excellent. What does filter do? Given a collection or a container, we call filter.
And it applies a filter function to every element of the
Good.
container.
Okay, and so it returns a container of elements that were drawn from the original collection, such that for each of those elements returned, that function was true. They passed the criteria. We're giving it a function that's a criteria, that's a condition, that's a predicate. It states, are you passed on or not, true or false? If it's true, then they're reflected, that value is included in the container that's returned, otherwise not.
These are inbuilt functions.
These are supported for collections in Java across the board. So for streams, for arrays, for lists, for maps, for dictionaries, etc. Okay, for ranges, etc.
Question.
Yes.
This is, I guess, sort of computational question. If you wanted to filter on two conditions,
Yes.
assuming you're doing this in a stream or some lazy implementation, is it better to have two filters, each with a single condition, or one filter with two conditions?
It's a good question. You could do it either way. If you're doing it on a stream, it's going to be pretty similar performance. Okay, it's very similar performance. If you're doing it on an array, then or some other structure that's not lazy, then you are after each one going to be recreating a full data structure of successive results, and that could cost more memory. So it'd be more efficient to do at once in a single filter. Okay. We also saw reduce. What was the job of reduce? What was the job of reduce? It took a function as well.
It was to apply a function to two successive elements.
Good. It takes in a function that can be applied pairwise to successive elements, sort of an accumulated value and a value from the collection. And its job in life really is to sort of summarize the values in the collection, to kind of add, for example, add them up, or take their max, or take their min, or take their mean, or whatever. It operates on successive values and returns back a single value, not a collection, not a container, but a single value.
So
now,
I could use reduce, for example, to calculate the variance of a population.
Yes, that's correct. Yes, yes, you could. Yeah. Mm-hmm. Yeah. So, and there'd be a bit of texture on how that would be done because it involves. But yes, you could do it with the e of x, the expected value of x squared minus e of x. Yeah. Okay, ladies and gentlemen. Flatmap is what we're going to talk about next time, or this time rather. What did we group by? We also saw last time. What does that take as an argument? It takes a function as an argument. What does that function do? Well, it specifies the group into which so the job in life of that function is to be given an element to the container, and for that element to return a value that indicates which group it belongs to, which group it belongs. And it gives us back a map, a mapping from those group IDs to the things, all the things that fell in that bucket, fell in that group, that were a part of that group. It's container for that group. It kind of, for those who have seen SQL before, it's like group by in SQL. It basically divides up our container into different buckets, where each bucket is associated with a certain key as returned by that function we've given it. Okay, So that function goes through each element, and it classifies into which bucket it goes. And then it returns to us a mapping between the key for the bucket and the bucket contents itself, the set of all elements that went into that bucket. That's what this map does. For each K, it has a whole container associated with it, the set of all things that had that. So when we, remember, classified words by length, we might group by their length, and for length 1 would be all the things of length 1. I, A, for example. Length 2
We.
would be 2. It would be we, and of, and at, etc. Yes, Kurt.
Doesn't the group by return a container of maps?
No. it's
No,
a map
it contains a
of
map of containers. A map of where
But there's more than one key,
there's more than one key.
right? So
You
there
bet.
should be a container of maps of containers.
No, because a map itself has multiple keys.
Mhm.
Oh, so,
Yeah,
right.
yeah. It's just how map is defined. I
I find
Yep.
something that's very unfortunate is that they use map as a verb to talk about mathematical transformations. They also
Yeah.
use map as a noun for data structure.
yeah, it is kind of unfortunate. Yes, I agree with you. Okay, ladies and gentlemen. Ladies and gentlemen. Now we will look at Flatmap, which we used. Where did we use that? Where did we use Flatmap?
Last week.
Well, we actually used it as recently as Tuesday in this very room.
Yep.
Okay? Flatmap. Let's go see where we used it, shall we not?
Right there.
Okay, so it was going back through down memory lane. Here we go. Okay, you see I have fun at home. Pulling examples for this class. Okay, ladies and gentlemen, do you remember this? Across the mists of time. Mumble.
Not that
Of course. I need to import. What do I need to import? Scala.io. Boom. Boom. Okay. Do you remember this?
Yeah.
Okay. So, how could you forget, right? Here, ladies and gentlemen, we drew lines from a file. For each of those lines, we converted to a stream of lines, and then we did a flat map here. And I kind of waved my hands about that. I kind of flapped them, okay, about the flat map. Let's try to cut through this flapping now, okay? Ladies and gentlemen, so in order to unpack this, I'm going to go and I'm going to change this for anyone who has this in their buffer, their history. I'm going to change this to to array. Here. Remember, you have to be in the same folder as that document, or else it's not going to find it. What are these things here? Here's the command I just issued. What are these things here?
Unique array.
These are these tokens, as Scott designated last time, and a fine term for them. Basically, what's happened is I went to get the lines. Let's go back even further. Let's go back. This is a great thing to do, by the way, when you're trying to figure out these, is to kind of go back. Here's getLines.toArray. What are these things? These are successive lines in that file, are they not? These are, a thesis submitted to the College of Graduate Studies and Research and partial fulfillment of the requirements, right? Yeah. Okay. Ladies and gentlemen, try as you'd like. Unfortunately, there's no Scala command that's going to easily give you. You could play around. Scala is powerful, but it won't automatically generate your thesis for you. So you can hand it in. Okay.
Partial fulfillment.
Yeah, okay, ladies and gentlemen. So this returns an array of lines, and then what are we going to do? We're going to do this flat map. So this is this array of lines, and we are going to split each of those lines according to this so-called regular expression. Now, if you're not familiar with regular expressions, you are advised to go to a book and read up on them because they are incredibly practical, incredibly useful, of direct relevance for data processing, and they are fairly easily mastered in a way that lends delight to your life. Okay? So what we are doing is we are taking these lines, and anything that is not in the range of an alphabetic character, A through Z, and unfortunately I've imposed an English hegemony here. Anything that is not in this range, any character that is not in that range, will be ground for splitting into separate words around it. Okay, we will divide. We'll take this out, and then we will generate a college, and then we'll have a separate one that's a token. And it's like it interprets this almost like you could imagine splitting a CSV file, a comma-separated variable file, just saying, okay, split by the comma. And so the things on either side of the comma become separate things. The comma itself is thrown away. So this itself is thrown away because it's not in this list. This at sign is thrown away. This comma is thrown away. It takes the things on either side. So this it's split. It'll be splitting here. This thing is thrown away, and it's splitting here. It's getting this. This is going to be thrown away, and by splitting, and then it's going to do this. That's what that does. Now, how does that happen? Well, ladies and gentlemen, I'd like you to try the following, okay? I'd like you to try the following here. Try this. Do this, okay? And I will go and type it into my browser here, okay? Well, okay, we could do this in several ways. Maybe we'll do it just since you have those. Time is getting tight, and you have those things in your browser. I mean, in your thing here. I will just do it here. Suppose we said, instead of Flatmap, suppose we said map of this. Map. What would happen? What would happen? So again, what do the lines look like? This is what the lines look like. Suppose I said, instead of Flatmap, I said map.
Count each of the words.
Well, okay, there's going to be counting, but it's going to go through. Let's consider the very first line here. This is the very first line. What's going to happen? We're going to map. The map is, remember, the map is applied to each thing in turn in the container. This is the first thing at the container. When we apply that map, what's going to happen?
That's a two function that splits itself.
It's going to split that line into subthings. And where are those going to go? Well, map returns a single value. Do you remember that? Map returns, remember, you pass in a function and it applies that function to each element. So what is this function going to return here? It's going to actually return a collection of strings. So we would get something like this, ladies and gentlemen. Now we would have something like this. The first line, this guy up here, this very first line is now divided up into an array of words of that line, which is great, but now we have an array within an array. The second line here, ladies and gentlemen, collection tool and accompanying configuration, that gets turned into an array as well. Remember, map treats each element in turn in isolation. It takes a function, and the function is applied to each successive element to get the corresponding element of the return collection. So this function is this split thing. It's going to split. And it is going to split whatever the element is, the line there. So it's going to split this, and guess what happens when we split that up? We get an array out. Well, let's try that. Let's suppose that you were to apply this thing. Don't take my word for it. Watch this. Okay, suppose we were to split this. Lickety split. Okay. Oops. Okay, I'm sorry. Oh man. Oh, this is a bad thing because it's applied. Okay. Let's do array of lickety split. Okay. Sorry. we could do that, but that's a little bit more wording. We'll just apply split to that directly. Split, okay? Lickety split. What do you think will happen? It'll give an array of lickety and split, right?
So,
So-
what Flatmap does, it sort of breaks down the arrays that you normally get returned by map.
Yeah, so that is correct. So Flatmap flattens the array. So instead of being an array of arrays, it turns it all into one array. It flattens it out. Instead of being an array of arrays, it squishes them all to one level. So it takes all of those that were, so remember when we did this, we got back, when we did this with simple map, when we parsed each of those, we got an array for the first line, an array for the second line, an array for the third line, and Flatmap collapses those all into one array for the entire thing. Yes, Kurt?
Does it flatten a map or does it map a flatten? Like which one does it do first?
It flattens the result of a map.
So it does a map and then it flattens it.
Correct. So it produces, conceptually, yes. It produces this and then it actually flattens it. Okay?
Is that produced in memory? The array of arrays and then it rearranges it?
Not
Not if you're using streams. It'll produce it incrementally, as we will see
That's cool.
in the fullness of time. Now, Flatmap, Flatmap seems like, the first time I saw it, ladies and gentlemen, I have to confess, it seemed to me kind of like a hack. It's like, this is an inconvenience. It puts arrays in arrays, so we'll flatten it. Turns out it has profound implications, and we're going to revisit this soon enough in the context of monads. Okay, Flatmap is one of the two key operations for monads, and the fundamental difference between map and Flatmap is the fact that map. How does this signature differ from map? Can anyone tell me? How does that signature differ from map? What does map? So both cases, they take in a container of E and they return a container of F. But what's different here? Yes, Scott is onto it. What is it?
E maps to F and returns
For map.
And returns container F, where Flatmap maps to the container.
To a container of F. That's right. And so in our case, what is this container? What was that thing we just saw?
Each array of lines.
So this split returned itself an array. So the container of F that it refers to here was array of strings. We had a string mapped to an array of strings. That's what split gives us. Split.
Or split returns a container.
Calling split on its argument. The underbar is just is just a sort of name for the for the value here. We could have said line, arrow, line, dot, this thing. Okay. For those who are not native English speakers, as way of education, lickety split means really fast in English. Okay, so if you say that to others, they may be impressed by the knowledge and antiquity of your diction.
Antiquity for sure. It's English.
Yeah, just like spiffy, or do it in a jiffy.
Yeah.
Do it in
You
a
also
jiffy.
spelled it
Yeah.
wrong, so
I think it's lickety.
it's Lick, lickety.
Not lickety split.
Yeah, lickety splits doesn't mean
Yeah, no, sorry, folks. I abused your English trust. Okay, lickety split. Okay,
Let's address this concern right now.
okay.
Also, I'm not sure it's hyphenated, but I'll defer to you on that one.
Yeah, I'm not sure, but I needed it to be to prove the point, so I declared it such. Okay.
I have a question.
Yes.
A bit I wanted to know because I see a lot of similarity between Scala and Hadoop.
Yes.
So
Yes,
is it-
absolutely.
Scala was basically built to take some of the ideas from Hadoop, or
No, Scala. Scala was Scala or Scala, either one, was designed to allow for scalable processing in a programmatic context, and that includes large amounts of data, which is the goal that Hadoop addresses too, handling very large amounts of data. Both of them draw on knowledge that was been built up out of research over decades about what are scalable data architectures based on the framework of functional programming. And so both of them recognize the fundamental scalability of functional constructs and higher order functions like map, filter, and reduce. And so they're not, it's not like they are totally independent, in their creation. But I would say that neither one directly inspired the other, but they came out of a body of understanding of what works in a large data context, for example, that was common. Okay, and these are ideas you have to understand that have been circulating for the past 25 years at some level. The realization of how we can build scalable systems that can handle large amounts of data and do so in a way that takes advantage of parallelism. Okay, and we're going to in fact go and talk about that next, which is parallelization implications of map, filter, and reduce. Okay, so these constructs that we have been using, which afford us a beauty that I hope you will come to appreciate, even if right now beauty is not the foremost emotion you see when you see this. There's a beauty there. It's orthogonal. It's modular. We can substitute small bits of it to just change one little thing and get something that's also really useful, but reuses the mechanisms, but gets something that's quite distinctive. We can divide up our computations into well-defined pieces, each of which can be understood in isolation. We can build these kind of modular pipelines, which afford us the chance to kind of write functions that have clear separation of concerns. There's lots of software engineering benefits for describing things like this. But, ladies and gentlemen, there's also profound benefits when it comes to performance. And one of the big ones, not the only one, we'll soon be talking about laziness as a big benefit, which allows us to save memory. One of the big benefits is parallelization. So maps and filters, ladies and gentlemen, if you think about them, they involve executing a function, evaluating a function passed to each of them on each elements of a container, right? I mean, think about it. So map here, here takes a function in and applies it to each element of this container in turn, right? Filter does the same thing in order to determine whether or not each successive element is to be included in the resulting collection, right? That application of this function to each element in turn of the original container, it can be parallelized in a embarrassingly easy way. Yeah, it's embarrassingly parallel. Meaning that we could have different processors responsible, or different computational units, different GPUs, responsible for subdividing up the elements of this original container and applying this function to that particular set of elements. So we might have, ladies and gentlemen, here, and I'm going to use the board to the detriment of the folks who are attending here over the internet, and I regret this. So we might have, our container be composed of many, many items here, and there's some long number of items. And in data science, it wouldn't be unusual if these are millions of items. Think about the types of data Narges processes to recognize smoking behavior and e-cigarette use, and these might be millions of accelerometer records, right? And if we want to apply a function, each of them, to get back a new container here. This is, x0, x1, x2, and this is what? If we have, f of x0, f of x1, f of x2, etc. Now, if we have a bunch of processors available, maybe we only have 4, right? Maybe we have the first 4, the 4 take, these segments, these segments, these segments, and these segments of this collection, and apply, each of them is responsible for applying F to a particular element, right? So that can be parallelized more or less directly. And the same thing with filter, right? We could apply to each element, and we could determine, is that element got to be reflected in the final set? And there's more work there because we need to condense things down and sort of coordinate that. But the fundamental thing is it can be parallelized. Okay? Yes, Scott.
And so if you stream something, you can parallelize it all the way down to where it can't be parallelized.
Well, with streaming, we have the additional component, as we're going to see next time. It's going to be our main topic next time. We're going to have the additional component of wanting to keep things in memory as little as possible. With streaming, however, we can pipeline this whole series of operations in a way that allows for certain components, for example, to be mapped to a processor, another processor, if we wanted to. We also can do it in a way that takes advantage of successive transformations in memory rather than producing new collections. Okay, now with reduce, the situation is somewhat more tricky yet. Because with reduce, we're not getting out a whole collection. We can't just, in isolation, apply F to each of these elements. Instead, we're going to need to summarize. But the beautiful thing is, and unfortunately we're past time for me to let you out here, but what we're going to be able to do with reduce is to be able to have different processors summarize different subcomponents of this and do so in a way that allows them to be combined pairwise. So we might have these two, one processor summarize these, get a summary, maybe it's the max of these. Maybe this one summarizes these, it takes the max of these. This one takes the max of these elements, this one at the max of these elements. And that yields two maxes, which can then be further processed here. Now, in general, I've done this with 4 processors. We might have 4,000 processors. You think about a GPU. Or we might have a whole farm of machines operating on billions of data items, in which case we may have several layers of this reduction. We may have 5 layers. But what determines how long it takes, ladies and gentlemen, on an overall scheme, we're going to be having to consider not only the time to process each little set of elements here, but also the number of stages here, which is going to be proportional to the log of the number of units into which we've divided it. So here we're going to have a sort of log of n. And if we think about this as starting with pairwise down here and successively growing up from there, and we're going to have some number of data elements, capital N here, and then this will be a tree of depth, a depth log n, okay? And so what this means is that while we can't do something quite as embarrassingly parallel here, where we just apply F in isolation to each element using a separate processor, what we can do is have with sort of an intelligent coordination, an intelligent division of the work, we can end up having a very favorable scaling with this, where we can still parallelize a whole lot and successively combine things in a way that's still very efficient and scales favorably with the number of elements. It doesn't scale in a way that is highly adverse with the number of data items. Now, I could go into this more, and I think I will go into this more in a later lecture, but because we're over time now, I just wanted to give you a hint of it. The point is here, parallelization is one of the key benefits that comes out of decomposing a computation with these map, filter, and reduce. It's the ability to farm out those computations to a number of different computational units that can operate in parallel, or mostly in parallel, and whether it's map and filter, which are embarrassingly parallel in the application, or reduce, which requires somewhat more coordination but can still be effectively decomposed, we get a great deal of parallelization benefits out of this, okay? And this is a topic I'll likely come back to with quite a few more slides and explaining more detail the mathematics of this, but it's of direct relevance for large-scale data processing. So you should realize these constructs are of great value for, in the context of software engineering. They're of great value in terms of decomposing problems. They're very flexible and powerful constructs, but they also have great benefit when it comes to parallelization. And just to give you a fleeting glimpse of that here, something you can literally type into your command here. If we had this handled as a 2 array, for example, here, we could perform this computation, and we could turn it into a parallel array, an array set up for parallel operations. In which case, so what did I do here? Okay, sort with is not a member, of parallel sequence. Okay, fine. I'll just do it with this. So we won't do with the sorting. So this is now being farmed out to different processors, the processing of these lines. Okay. This par basically says do this with a parallel data structure that allows for efficiently dividing it up into different processing units and allowing the subsequent mapping to be done by those different processing units. Okay?
So why the other way when you have this? Why even do it the other way when you have a parallel?
Because parallelization, great question. Parallelization is not always going to provide a speed up for certain lines of work. Also, as you saw, the parallel implementation don't necessarily support as directly some of the functionality, okay? So it's awfully easy to do. You can do it a large number of cases, but you don't want to do it trivially because preparing it for parallelization actually does require some work. And if you're not going to take advantage of it in a serious way, if you're not dealing with the data volumes needed to do it, you're dealing with a very iterative inner loop or what have you, it wouldn't make sense to sort of just casually make it parallel, okay? So it does have some implications in terms of trade-offs involved. But it is also something that's very, very often desirable when you're dealing with large amounts of data. Okay? So, ladies and gentlemen, thank you for your patience. Next time, we're going to be going into this issue of laziness. We're going to be talking about two types of laziness. We've already seen one of them, this by name parameter here. But we'll see how not only can we call .par on a collection to make it parallel, we can call .view to make it lazy. Okay? And this is going to have profound impacts on conserving memory in terms of keeping down the amount of memory that's required by our computations. And we're going to have some fun exploring streams and defining streams which allow us to separate out the specification of a computation from its actual performance. Okay? So we'll be putting together some parallel, lazy computations next time in the form of streams. Thank you very much. And I will be posting a little challenge exercise for next time. Okay? Thank you.
Is the reason that Flatmaps work well with monads is because you retain all the metadata from the monad in Flatmap?
Yes.
Because it's
Yes.
the same container?
Yes. I'm not a swearing man, but if I were to swear, I would say yes, it is great. And not only that, in Scala, you can perform the operations on flat maps in a way that on monads, the flat maps and the other operations on monads in a way that hides all the metadata. You just perform it as if you're operating on the values, and it keeps track of all the metadata
Like how it
with
changed?
those, like the provenance data, etc. Yeah, automatically behind the scenes.
Wow. It's all the software engineering implications.
Oh, it is beautiful. It is beautiful. And I want you folks to glimpse the beauty, okay? So we're working towards that. We'll be hitting monads probably in a couple more lectures, okay?
So excuse me, I have a question.